All right, let's dive in and do some chemistry, right? Atoms, molecules, this is what you signed up for. So we kind of mentioned that the investigation is like the chapter. We're going to investigate atomic structure, and these experiences are like each section of the chapter. So here we're going to look at the particle nature of matter. And so first we know that matter is anything that has mass and takes up space. So you matter, you have mass, and you take up space, and you just matter because you do, because you're a person and you're kind, and you just matter to this world. It wouldn't be the same without you, right? Now, obviously, in your workbook, you would have a chance to read through this ahead of time, and maybe you underlined or circled things that seemed important to you. And here, I'll kind of walk you through maybe some of the highlights or the biggest takeaways from the unit. Atoms are the building block of matter. We can combine atoms to form molecules or different forms of matter. I mean, right now on the periodic table, there are 118 elements. And an element is just a simple form of matter that has a characteristic set of properties. But it boils down to the atoms of a particular element all being the same. So neon is an element. It's on the periodic table. And all atoms of neon are the same, which is then what gives neon its characteristic set of properties. It's a gas, it glows when we electrocute it, as opposed to maybe something like sodium. Sodium atoms are all the same. They have a characteristic set of properties because the structure of a sodium atom is the same. Protons, neutrons, electrons, all that good stuff. Now, sodium atoms are different than neon atoms, which is why they have different characteristic sets of properties. If you know anything about sodium, which if you don't, you eventually will, we'll play with some sodium. It's a great element. It's a metal, which is obviously different than neon being a gas. And of all metals, sodium is kind of unique in that it's a metal that will ignite when you put it in water. So what are we going to do with it? Throw it in water, right? Get out a fish tank and we'll see what happens. But yeah, atoms are the simplest form of an element. They're the simplest unit. We can break elements down into their characteristic atoms. But again, if there's 118 elements on the periodic table, that would mean that there's 118 different kinds of atoms that we know of today. But obviously there's a bazillion different forms of matter. And that's why we can combine matter into these things called molecules that also have new properties. The symbols are on the periodic table. They help us to represent the elements. And then here they just give us kind of an example of modeling atoms of different elements using marbles. So marbles as models, which is one of those science and engineering practices that scientists have to do, especially when it comes to something that we can't directly see. Like nobody's been able to see an atom, not even with the greatest microscopes. You can't see down to the individual atom. But we can study properties of different materials and different elements, and from there we can make models of what we think the atoms look like. You can visualize atoms as tiny spheres with different sizes, much like these marbles. And so kind of like the marbles are different sizes, some are bigger, some are smaller, and we think of that as being a similar representation of atoms. That hydrogen atoms are pretty small, gallium atoms would be bigger. Spheres as models. Here it says scientists often use spheres with different colors and sizes to represent atoms. So throughout this text and in your previous science classes, I'm sure that atoms have always been represented as little circles, little spheres, and if it's in color, we often represent the elements with different colors. And we can also get a little more sophisticated and show differences in sizes and try to make the scale a little bit more representative. That, yeah, hydrogen atoms are small, so we'll make them small little spheres. Which then brings us to this third question. Science and engineering practice. like developing models and thinking about limitations of a model. What is a limitation of using marbles as models for atoms? And so there are some things that work great. That, yeah, we can represent them as little spheres, and marbles can come in different colors to represent different elements and different sizes to try and represent what atoms are big or what atoms are small. But could you think of anything that might not be 100% accurate about using a marble as a way of representing an atom? And again, here there's not necessarily a right answer or a wrong answer. And last time I checked, if you can't see an atom under a microscope, I don't know that a marble is a good representative of like the true size of atoms. Marbles would be made of millions and billions and billions and trillions of atoms. But we're, even though not to scale, we're still trying to represent the size and maybe the relative, like radius of atoms, like hydrogen relative to gallium. Oh yeah, gallium's bigger. Obviously in real life, they're not that big, or they're not as big as a marble. But maybe you thought of some other ideas too. We kind of mentioned the term molecule then, that a molecule is when two or more atoms combine. So the word molecule is a very general term, just two or more atoms combine. And they're held together by bonds, and eventually we'll study bonding quite a bit. How are they being held together, and is it a stable bond, or is it easy to break, hard to break? And so they show us this picture here where we can think about modeling molecules. These models show how bonded atoms can be represented as joined spheres. Okay, cool, I got that. So it's like trying to represent two atoms joined together. We don't always show the bonds, and sometimes we just kind of like show the atoms kind of tucked next to each other, and that's fine too. Some molecules are made of the same element, and others are made of different elements. When they have the same element, so an example might be like nitrogen, like this nitrogen, two atoms, same element, it's a molecule. More specifically, you might see the term diatomic. Diatomic molecule. We might use diatomic. Di meaning two, and then atomic referring to atoms, and more specifically, two atoms of the same element, like nitrogen. Another example would be like H2, hydrogen, O2, oxygen. They just come in nature paired together. And eventually when we talk about bonding, we'll learn that there's kind of a cool reason for it, that hydrogen atoms alone are not very stable. But when two hydrogen atoms can bond together, they are much more stable in nature. And nature favors stability. We always want to do whatever we can to put matter in a more stable state. So you might see that term diatomic molecule, and it really just means that the atoms are the same. Now, maybe more specifically, something like water being made of two different elements, this is often referred to as a compound. So it's still a molecule. Again, molecule is a very general term. Anytime you've got two or more atoms bonded together. But we might break that into two different groups. Like these are both molecules. We might call nitrogen a diatomic molecule, meaning that it's two atoms of the same element. And more specifically, I might refer to water as a compound. That indicates that there are different atoms. There are atoms of different elements that join together. And again, we often use the symbols. I mean, sometimes it's helpful to look at a picture of a molecule, and there are times when you want to know its shape, like, you know, how big is it? How are the atoms arranged? Because the shape or the orientation of a molecule is going to have a lot to do with how it interacts with other forms of matter, other molecules. But sometimes we're cool with just the symbols, and so we might refer to just the chemical formula H2O for water. And so you might remember these little numbers are called subscripts. So like this little 2 in CO2 is called a subscript. And it just means that there are 2 atoms of oxygen. Now we don't always write it like C1O2. And usually we kind of leave off the 1 if there really is only 1 atom of a particular element. So if you put a 1 in, I'm not going to mark it wrong, but obviously you don't have to put 1s in. But you have to put in like a 2, 3, 4, or whatever. Then that indicates how many atoms of that particular element are bonded together in this molecule. Or in fact, here in the middle, carbon dioxide, ammonia, and methane could all be referred to as compounds as well. These guys are all examples of compounds because they all have different elements joined together. And those different elements are shown in different colors. Like I see that, like the carbon, since there's only 1 atom of carbon in carbon dioxide, it must be kind of this darker bluish black atom in the middle. And then the oxygen, there are 2, so that must be the red atom on the outside. In ammonia, there's 1 nitrogen, that must be the light blue atom in the middle, and then the 3 little white atoms must be the hydrogen. But then when I show methane, the hydrogen atoms are the same, to show that obviously any atom of hydrogen is the same. So we show them with the same color and the same size. Now, later on, we'll draw pictures of molecules where we'll try to show the bonds. And so then we might use like dashes or lines to show the binding force, the chemical bond that's holding the atoms together. And you may have heard of things like single bonds, double bonds, triple bonds. And that's important to indicate eventually, because as you might guess, like going from a single bond to a double bond to a triple bond, like triple bonds are really strong. And so there might be times when that would affect the properties of that substance, and I might want to indicate that in my picture that, ooh, this one's a triple bond, so this is going to be a really strong bond. Cool. So then, number 4, a science and engineering practice, developing a model. Use colored pencils to draw models of a chlorine molecule and for a hydrogen chloride molecule. Use the colors and relative sizes from the atom key on the previous page. The atom A, I think that's supposed to be the atom key on the previous page. Okay, so maybe you had colored pencils or markers or crayons or whatever, or maybe you just kind of drew them and shaded them in on your own. But if I go back, I'm looking for the chlorine and the hydrogen. So it looks like the hydrogen was kind of a small white atom and the chlorine was a little bit larger green atom. So if I were drawing chlorine diatomic, I would maybe do like, I don't know, chlorine. And if you didn't put like the symbols in there, that would be fine. Maybe something like that would represent a chlorine molecule, a diatomic. I might put that in there too. Here's another example of a diatomic element. Or molecule. And we could use molecule, element, diatomic, meaning that there are 2 atoms and they're both the same. For the hydrogen chloride, hydrogen was kind of a small white atom, and because I'm not going to write white on white, maybe I'll do black. And so I'll show kind of a smaller hydrogen, and then I would bond that to a chlorine. And I'll try to make the chlorine about the same size. That one looks a little bit bloated, but you get the point, right? So hopefully you do something like that. We're just looking at different ways to model atoms and show their relative size, show molecules, and what kinds of elements are bonded together. Are they the same elements? Are they different elements? And then we try to indicate that either with different colors or here by kind of showing the relative size. Cool. And so finally in this section, we're going to look at communities of particles, groups of atoms or molecules, the attractive forces that hold the particles together, and the motion of the particles. And I would even maybe add to that the energy level of the particles, motion of the particles, and energy level of the particles determines its state of matter. And so you've heard of solids, liquids, and gases. It's not the first time you're hearing of those terms, I hope. And so there must be something different about the arrangement of the particles, the motion of the particles, the forces of attraction in between the particles, the energy level of the particles that can affect the state of matter. And so water is a good example. We're pretty familiar with water being in its solid, liquid, or gas state. And so the other day we were trying to kind of model what we think gas particles might look like. And so here if I'm drawing little water molecules, water is H2O. So we've got the H2, that must be like the two little white circles, and the O is the one bigger red circle. So even without knowing much about atoms or the periodic table, I'm guessing that oxygen atoms are bigger than hydrogen atoms, just by looking at the model of the molecule. And so water in the gas phase, water vapor, is obviously pretty common, and we know then that the particles are far apart, they move freely, they usually have like the highest energy level of the three states of matter, that we say that gas particles are constantly moving and bouncing all over the place. They bounce off the walls of their container, they bounce off each other, they completely fill a container, but there's a lot of space in between the gas particles, high energy, and they move freely throughout their container. All right, liquid particles then have a little bit less energy. I mean, liquid particles can still move around, and so they're just a little bit closer to each other, and that makes me think that the attractive forces that must hold the water molecules together are a little bit stronger when we get to the liquid phase. That for some reason the water molecules are a little bit closer to each other, and so they still kind of move, but they don't like fly all over their container. They take on the shape of their container. So I could pour 100 milliliters of water in different shapes of containers, and it's still 100 milliliters. It's only a certain amount of water molecules, but because they can move a little bit, they'll take on the shape of the container. It's just that because the attractive forces are a little bit stronger, they don't completely fly all over the place and take up the entire volume of the container. And then finally we've got the solid phase. So often there's a very fixed pattern, a very organized pattern in some solids. Water would be a good example of that. Crystals are a good example where there's a very organized pattern of molecules or atoms that make up the solid. They're pretty low energy. There's not a lot of movement, and maybe the particles vibrate slightly. And obviously then if the particles are often pretty low energy and they don't have a lot of movement, and they're pretty close to each other, we think then that there's pretty strong attractive forces holding the particles together in the solid phase. Probably the strongest of all three phases. Whatever the glue is in between the particles of a solid, it must be the strongest. And in a gas, it must be some kind of a really weak glue in between the particles, because they're pretty far apart and they move all over the place. They're not very attracted to each other, as opposed to a solid. So usually that's how I think about solids, liquids, and gases, and we kind of refer to the particles by their energy level, by their arrangement. Are they close to each other? Are they far apart? Their movement, can they move freely? Are they pretty fixed and close to each other? And then also the degree of attraction in between the particles is a big indicator of what phase of matter we'll be in. But then 5 is kind of an interesting question. Science and engineering practice, constructing an explanation. So scientists make observations of matter, and then they try to figure it out. They try to explain their observations. Density is a measure of mass per volume. And maybe you've done density calculations where density equals mass over volume, something like that. It is a measure of how much mass is in a given volume. And so maybe if I had, like 100 milliliters of water versus 100 milliliters of a different liquid, like maybe an oil or like an alcohol or something. If I had the same volume and I put them on the electronic balance, I could find the mass, and then whichever substance had the highest mass per volume would have the highest density. Now that could mean a couple things. It could mean that the particles themselves are just really heavy, so that they're just very massive. It could also mean that the particles are very close to each other, that in a given volume, if the particles are really close to each other, there would just be more particles. But now this is interesting. Maybe you've heard that in order to float in water, something has to be less dense than water, or whatever the material is. It has to be less dense. And so when you think about phase, usually I think that the solid phase would have the particles really close to each other. And so I would think then that the solid phase would have the most particles per unit of volume, which if there's the most particles, it would be the most massive, which would then create the most dense phase. And for most substances, that's the case. But water is a little bit funky. And so it says, use the models to explain on a molecular level why ice, solid water, actually floats in liquid water. And so if it floats, then there must be something about this versus this that's not maybe normal for a given substance. Did you kind of catch it? That if density is mass per volume, let's say I measure a certain volume. And so I don't know, maybe it's like, here's a given volume. I don't know what it is, 10 milliliters, 100 milliliters. And let's say I measure the exact same volume. Okay, so if volume is the same, let's say I pick the same volume of solid ice and liquid water. Do you see the difference in mass? Do you see the arrangement of the particles is different? And this is not normal when we compare a certain material in its solid and liquid phase. Usually, the solid phase has the particles packed really tight, and there's more particles per unit of volume, which then would make that phase more dense. But do you see it's different with water? Water molecules in the liquid phase that are free to move actually kind of like fill in all the nooks and crannies in between each other. And they're more dense, not what we would expect. Water in the solid phase forms a very organized crystalline pattern. And it ends up that there's actually a lot of like empty space in between the water molecules in this crystalline pattern. And maybe you can kind of see, like they're showing here some water molecules kind of all together. Let's see if I can make this. Here's some, and like here they would be in the same arrangement. Kind of catch that? Like they're in a very organized pattern. But there's a lot of little air pockets in between the water molecules in the solid phase, which then means that solid water is less dense than liquid water.